Good day everyone. We are still in module 6. If you remember from our previous lecture, we have looked at the multi-layer neural networks. We now know how does a multi-layer neural network or multi-layer perceptron look like. There are input neurons, hidden neurons, output neurons, and you have to decide how many input neurons you would need, how many hidden neurons, how many hidden layers, and how many output neurons for a particular problem that you want to solve. We have also looked at the logistic activation function, and most importantly, we have studied the backpropagation algorithm. And now you know how to derive the backpropagation algorithm to adjust the weights and biases. So even though the derivation here is shown for output and hidden weight adaptations, you have to know how to derive the weight adaptation for the biases as well, BHJ and BOK. And here is the summary of the adaptation of weights and biases. And we have looked at the training steps. First, you have to obtain a training data with encoded output, which means your output has to be suited with the artificial neural network. So I've said that if you're using your artificial neural network for classification problems, the output has to be encoded because the neural network does not give you non-numerical output. It always gives you numerical output. So if you have a few classes as the output, then you have to think a way how to encode your output so that it will be suited to artificial neural network. And I've given you a few examples with answers. I really want you to try all this. So today, let's look at how we can design and build an artificial neural network to solve the NIST database, MNIST. So this is the modified National Institute of Standards and Technology database. It's a large database of handwritten digits that is commonly used for training various image processing systems. So it contains 60,000 training images and 10,000 testing images. So you can Google this information and you can also download the database. So basically the database consists of pixel values of handwritten digit images. So these are handwritten digits and the database contains the pixel values of these images, 28 by 28 pixels. So I have downloaded the database and this is how it looks like. It has, first of all, this is the training data. You can download the training and the test data. The file is quite big, but not too big that you can't download. So if we scroll down, we can see that we have 60,000 rows or 60,000 data, right? And how many columns we have? We have we have 785 columns of data. So the first column is the number or the digit that an image represents. So each row from here till the end is an image. So we have From here till the end, we would have 784 columns, right? Because I said each row represents an image of a handwritten digit, and the resolution of the image is 28 by 28 pixels. So 28 multiplied 28 is 784. Okay, so from here till the end, we have 784 columns. Those are the pixel values of our image, and this is the digit that the image represents. So the first row from here till the end represents number 5. From here till the end is an image of 0, handwritten 0, and so on. And these values range from 0 to 255. So 0 means black and 255 is white. And anything in between, from between 0 and 255, is different shades of the color gray. So how does the image look like? I've shown you earlier. This is how the image looks like. So using Python, so this is what we get. So 0 represents, 0 is complete black, and 255 is white, and anything in between you would get, like I said, different shades of the color gray. All right. So now the question is, how many possible outputs that we can have? Because these are handwritten digits, so we can have 10 possible outputs, right? From 0 till 9. So that is 10. But like I said, we have to encode this output. Even though this is numerical value, and conceptually our neural network should be able to produce numerical output, but because this is classification, from experience, I know that it will not work if we only have one output neuron. We still have to encode this information. All right, so we will talk about that shortly. And how many input neurons we should have. So like I said, from here till the end, I'm not going to scroll till the end. From here till the end, we have 784 values or columns. That because our each image is 28 by 28 pixels, 28 multiplied 28 is 784. Therefore, we have 784 columns. So the problem here, what is our problem that we are trying to solve? We would like to give an image to our artificial neural network, and our artificial neural network should classify the image accordingly, whether the image is digit 0, 1, or 9. So how many input neurons? So we should have 784 input neurons. So how does it look like? I have drawn for you. So this is how our artificial neural network should look like, the architecture, right? So we should have 784 inputs because we have 784 pixels. So this is new input neuron 1, input neuron 2, up to input neuron 784. So our capital I is 784. How many hidden neurons? This one we don't really know. So you have to try any number that you're comfortable with. So in our example here, I choose my input neuron to be 32. So capital J is 32. How many output neurons? So we have to talk about the encoding now. So because we have 10 possible output classes, we can use the one hot encoding method. So our output of our artificial neural network would be 10, so y1 up to y10. So if the image is handwritten digit 5, the output from the neural network that you should expect is 0.000010000. So you should train your artificial neural network such that when you give handwritten digit 5, you would get 000, this value, 0.00001 somewhere here, and then the rest are 0. If you give handwritten digit 0, which means the second row, you know the desired output is number 0 because this represents the image 0. But because we are using artificial neural network, the output has to be encoded as 1000, and the rest are zeros. So this is what we call encoding our output, and this particular method is called one-hot encoding vector. Okay, because at each time only one output neuron will be fired, or it will be as close as possible to 1, and the rest will be as close as possible to 0. So this is the architecture of our artificial neural network. Let's see how we can do this in Python. So first step, we have to input packages, and we'll be using Keras. So these are because the package, or the package we call it, Keras, comes with the data set. We don't have to import our CSV file. It is built in the package. So we just import mnist, and we can just load the data. Right. So this is how we load our NIST data into training and test data. And if we print the training data shape and the test data shape, we can see that the shape is 60,000, which is the number of data that we have, the number of rows, and it's 28 by 28. So it has already been given in three-dimensional, right? But this is two-dimensional. Remember, this is not in the package. This is downloaded from the original source. It is in two-dimensional. It is in 2 dimensions, right? But the data set in the Keras package is 3-dimensional. It's already sorted out according to the image pixels. And our test data is 10,028 by 28. And this commands is to plot, is to see what do these values represent. So we plot this, we get 504 and so on. So these are the handwritten digits that our database represents, our data set represents. Because we are using our multi-layer artificial neural network or multi-layer perceptron as this, it does not take two-dimensional inputs. It takes one-dimensional input. Right? You can imagine this is a vector, not a matrix. So we cannot give 28 by 28 data. We have to flatten it. So this is what we do. Xtrain dot shape, which means we from 28 by 28 we flatten it, and so that it becomes 784 by 1, a vector. So now if I print out the shape, we can see that the shape becomes this one, 60,000 by 1. Right, so now this is ready to be given to our artificial neural network. So, and I'm interested to see what is my first 5 training labels from our Y train, it's 50419. Let's double check. It is 50419. These are the labels. But remember, we have to encode this. And this is where we do that. We convert to one hot vectors by using the function to categorically. So we say that we give in our output, both Y train and Y test, and we say that we want encode this to 10 possible, 10 dimensional vector, right? 10 by 1, because we have 10 classes. We say convert Y train to a vector of length 10. So this is what we get. So number 5 becomes this, number 0 becomes this, and so on. So now this becomes our training and test output, right? Training and test input remains the same as we saw earlier after reshaping. So this is when we build our model. We create an instance of a sequential model. We add a hidden layer. We want 32 hidden neurons. Activation function is sigmoid, and the shape of the input is 784 by 1. This is our output layer. We have to mention or say that we have 10 output neurons, and the activation function is softmax. And if we look at the summary, we get this. This is the summary of our model. So how do we get 25120? These are the number of parameters that the backpropagation algorithm has to adjust, right? So this comes from these are our weights and biases. So because we have 784 inputs and 32 hidden neurons, therefore we have 32 biases. So we do have 25,120 parameters to be adjusted. So this function trains this is preparation. Before training, we have to mention what is the optimizer we want to use, the loss function, and the matrix. So this is where we actually train our model. We give in our training data. We mention batch size, how many epochs. Here I mentioned we need only 10 epochs due to time constraint. Validation splits 10%. And finally, once we have done that, we have to validate our data, which means we test our performance, the performance of the model on the test data. So that's why we supply X test and Y test. And the accuracy that we got is 91%, which is plotted here, 91%. And this is to plot the performance of the model while it's training. So this is what we get. So remember that we require 10 epochs. So for every epoch, the accuracy increases. And because we have mentioned that the training splits is 10%, what this means is that the training data itself is split into two again. So the 90% of the training data is used for training, the blue line, and the remaining 10% of the training data becomes our validation set for us to monitor whether the accuracy increases as well or not. If you remember from our machine learning model, when the accuracy of on the training data increases, but the accuracy on the validation data decreases, that means we are overfitting. So we don't want to overfit our model. So that's the reason we split further our data during training. So that's it for this video. I will upload these files on e-learning. Please have a look and try it yourself, and we can discuss any arising matters next time. Thank you.